Today's lesson is on earthquake definitions. So we're just getting the beginning earthquake definitions and fault examples out of the way, and then we'll get on to the other parts of the earthquake unit. So we're starting with the basic definition of what an earthquake is. An earthquake is just a sudden shaking of the Earth's crust caused by a release of stored energy. Well, where does that energy come from? You should know this from our previous unit. The energy comes from plate tectonics. Okay, the movement of plates is what builds up this energy. When you think of the plates, we talked about the North American plate and Pacific plate and all these big lithospheric plates that are floating on the asthenosphere, and they're bumping into each other and going away from each other and sliding next to each other. Well, don't think of these plates as having smooth edges. They're big, giant rocks, and they're really rough edges. And as they slide next to each other, they get stuck together. But the convection cells underneath them keep pushing. Eventually, the rocks that are stuck together can't handle the strain, and they snap. And when they snap, they release that energy in the form of waves. And that's the earthquake that we feel. And that's the basis for the elastic rebound theory. So you have your definition on the first blank there, and then I kind of skip down a little bit, and you look under the earthquake waves section on that first page, and you see the elastic rebound theory. It's what we just talked about here. So the plates on either side of the fault are moving in different directions or different rates, putting pressure on the fault and deforming the surface. Remember that these plates they don't have smooth edges, so they get stuck together. So here you see kind of the before, San Andreas Fault in California. The pressure builds, and it's going to start to deform. Now, you look in this picture, you say, wow, it's really deformed, there's going to be an earthquake. We should know, we should be able to predict it. Well, it's not going to be this obvious. There are some people that are looking for things like this, though, a deformation of the surface, to try to predict when an earthquake might happen. But it's not as easy as this picture may show. So the plates, you can see the edges of the plates, they get stuck together. The plates are moving in different directions, this one this way, this one this way. The pressure builds up. Eventually, the rocks can't handle it. The plates snap, and it releases that energy, which is the earthquake. And then if you look at it, each side returns back to its original form, just now separated. So you see the wall is back to being straight, but it's just broken into two pieces. And you see the little sheet got out. That's where this name of elastic rebound theory comes from. If you think of it like a rubber band, and you stretch your rubber band, you stretch, and eventually your rubber band's going to break. So here's my original rubber band. I stretch that rubber band so it's really big. The pressure is greater. Eventually, I pull it far enough and it snaps. And I feel that shock wave, the earthquake waves essentially, in my hands maybe. The broken rubber band, it's not this big though. The broken rubber band goes back to being this big. It's just broken. So maybe now it's like that. So it's the same size as it was before essentially. It's just broken. And that's what this is showing here. So the plates are going different directions, the pressure builds up, the rocks can't handle it, it snaps. The rocks go back to being straight, they're just now in different positions. Well, where do they break? They break at what's called a fault. So a fault is just a break in the crust along which the two sides have moved. There are three main types of faults that we're going to talk about. You can see them here. We're going to draw pictures for them too. There's a reverse fault, normal fault, and a strike-slip fault. That's what we're going to go through next. First of all, we have the normal fault. The definition is just a fault where the hanging wall slides down along the footwall. Okay, I know you don't know what hanging wall is yet and footwall is yet, but we'll get those definitions. You can see at the bottom. We'll get those definitions in a second. First thing though, before we do that, what I want you to do is flip your paper over and let's draw a picture of a normal fault. So find a spot on the back and just label it normal fault. It's a normal fault. And the picture we're going to do is pretty simple. Draw one side of the fault looking something like this. The other side of the fault is going to have slid down So it was up here, it's going to slide down, so go something like this. So this one slid down. That part of the fault slid that way. So this is like a side view that we're looking at, kind of like this. This one here, this part that slid down, that's the hanging wall. The hanging wall is the mass of rock above the fault plane. The fault plane is this angled line here. The footwall is a mass of rock below the fault plane. It's this one here. Now that may seem a little bit odd, but let me kind of show you a couple ways that you might be able to keep it straight. One way to keep it straight is think of it like there's a person on the fault, standing straight up. So a person standing vertically. Head's up here, body here, feet down here, arms here. Wherever their head is the hanging wall. So their head's there, that's the hanging wall. Wherever their feet are is the footwall. So there's the footwall. So the hanging wall slid down along the footwall. So that imaginary person stuck on the fault there is just a way to help you figure out which one's which. Another way which we can show you when we get to reverse fault is if you kind of think about this angle right here, it's not a very steep angle. It's not like an overhanging cliff. Kind of a nice little sledding hill is how I like to call it. If you see that gentle angle, you'll know that it's a normal fault. The hanging wall has slid down. Well, what has to happen to have the hanging wall slide down along the footwall? Are the two sides of the fault coming together, or are they going apart, or are they sliding next to each other? What would allow that fault to slide down? Kind of see a little hint right here. The plates are going to separate, and that's going to allow the fault to slide down because the two plates have pulled apart. So what must happen to create the normal fault? The rock must be in tension, so it's being pulled apart. So where would that happen? It happened at divergent boundaries. So when the land pulls apart, it allows one of them to slip down. We see in this picture here, there's a layer of rock here, and then here. This was a normal fault. There's your fault plane. Which one's the hanging wall? Which one's the footwall? Again, if you want to draw your imaginary person in there, you could do that. There's your head, there's your feet, your arms. The hanging wall is this one. The feet are in this one, so this is the footwall. So you can tell that the hanging wall went down. Look at these two lines. The hanging wall went down. So that is a normal fault. So it happens at divergent boundaries. Reverse fault is the opposite. Just a fault where the hanging wall slides up along the footwall. So you can write that for your definition, a fault where the hanging wall slides up along the footwall. And then find a place on the back, and we're going to draw a picture of a reverse fault. So go ahead and label your picture reverse fault. And we're going to be drawing this picture, but we can draw it a little bit more simply. I'm going to draw my fault block like this. My other fault block I'm going to put like this. Okay, something like that. You can see this one here, the one on the left in this picture, went up. Again, which one's the hanging wall, which one's the footwall? If I want to draw my imaginary person stuck in there, I can. Stand the imaginary person straight up. Oh, the hanging wall is where the head is. Footwall is where the feet are. So that is a reverse fault. The hanging wall went up along the footwall. Now, just a little side note here. Sometimes I'll say thrust fault instead of reverse fault. Really, it's basically the same thing. A thrust fault is very similar to reverse fault. The angle is a little bit more severe, though. Okay, so a thrust fault, if I would drew a kind of a little bit more severe angle, something like that. Okay, something like So basically the same idea though. The hanging wall slides up along the footwall. So if I say thrust fault, reverse fault, same thing. So what would cause this to happen? How would I get the hanging wall to slide up along the footwall? Now you kind of see your hint here. Okay, compressive forces. It's going to be pushed together. So where is that going to happen? It's going to happen at a convergent boundary. The plates are coming together and it's going to force the rocks up. Some pictures of some reverse faults. This one is Alaska 1964. This was a school, and you can see that it was forced up. There were some places that, remember, it was a 9.2 magnitude earthquake. There were some places in Alaska where the one side was raised over 30 feet higher than the other side. So it really raised the ground. You can see the school didn't do very well as it raised the ground. This was in Japan, the Kobe earthquake. This was a track, a school track where you'd normally run on. Not very good for running on. You can see that this land was raised, I don't know what, 5 feet maybe, during the earthquake. Again, we see this idea. If I draw my imaginary person in here, the head is here, so it must be the hanging wall. This one's the footwall. And you see the rock lines here that has gone up against it. So that is definitely a reverse fault. I said I would tell you about kind of, when you look at it, so if I go back up and look at my picture here, I said this is kind of an overhanging cliff. So when you see this overhanging cliff, think reverse fault. If you saw the nice gentle sledding hill, that was the normal fault. It's another little way to keep them straight, which one is which that you're looking at. The last main type is a strike-slip fault. The two sides of the fault slide against each other horizontally. So you see in this picture, and again, let's draw a picture. So on the back of your paper, find space, title it Strike-Slip Fault. What we're going to do is we're going to do a top view, so an overhead view of this fault. So top view. Could be very simple. Something like this. I'm going to say this one went this way, and this one went this way. Okay, it's just a side view of it. So the two sides are sliding next to each other, just like this is showing. Now, technically, they could be going the same direction, but at different speeds. That would make a strike-slip fault as well. Well, where would this one happen? What's going to cause the two plates to slide next to each other? Hopefully you remember that is a transform boundary. Here's some examples. Railroad track, not very good for a train because the boundary has broken it. This farmer's cornfield. You see these rows of crops have been offset by a strike-slip fault. So here's the fault line going right through that farmer's field. This is looking out from an airplane. So here's the airplane wing. You see this mountain chain has been broken into parts by some faults. One of the biggest, recent earthquakes, the Sumatra earthquake, in was it 2004? I think it was. The land moved about 160 feet during that earthquake. So imagine if you're like your neighbor's house, all of a sudden it's 160 feet away from your house. It can move a long way if those plates have been stuck for a long time. Then the earthquake can move the earthquake can move the sides a very large distance relative to each other. So could there be a fault that experiences both horizontal and vertical movement? Sure. We frequently call it a strike dip or dip slip or oblique slip, and then add the angles or distances with it. And I can show you an animation of that. Sometimes we'll also have a series of normal or reverse faults, creating landforms such as plateaus or basins. The ones that go up are called horsts. The ones that go down are called gravens. And I'm going to demonstrate all of these faults with fault blocks in class so that you can actually see how everything's moving. What type of fault is this? Okay, what type of fault is this one here? Look at the fault line. Fault plane is there. We look at the lines of rock. Put your imaginary person if you need to. hanging wall went up. So it is a reverse fault. We can see some animations of these. This one here is a normal fault. That one just slides down because the plates are moving apart. This one goes up because the plates are coming together, so it shoves it up. Again, we see kind of that nice gentle sledding hill. We see this overhanging cliff. Strike-slip fault. Okay, they're sliding horizontally or laterally next to each other. This one is oblique slip. This one does both. So in this case, it does some normal movement and some strike-slip movement. Okay, it's common to have that happen. I said the Sumatra one, it went like 161 or 160 feet horizontally, so strike-slip motion. It also went a little bit vertically. I don't know how many feet, 7, 8 feet, something like that, vertically. Imagine how big the tsunami could have been if it had done most of its movement vertically instead of horizontally. Could have been an even worse tsunami than it was. Okay, last thing we have for this section is we're just going to get our earthquake structure or our earthquake parts on. So again, find a place on the back of your paper and we're going to draw a picture, kind of like this. And we're just going to label our earthquake parts. So you can label it earthquake structure if you want. You could label it earthquake parts if you want. Doesn't matter to me. Okay, earthquake structure, earthquake parts. And we're going to draw a fault. I don't really care what type of fault you draw. Draw a fault. I'm going to draw one that looks like this. So which type of fault did I just draw? Hang wall slid down, so that's a normal fault. Okay, what I'm going to do is I'm going to put the parts on. First part I'm going to put on is the part down here where the earthquake starts. That is called the focus. So the focus is the point underground where the earthquake starts. And we'll get definitions here in a second. Also called the hypocenter. We'll talk about that. Think of hypo, that prefix means under, like a hypodermic needle, under the dermis, under your skin. Okay. Focus is also called the hypocenter underneath. Directly above it, so put a spot directly above it, right here, let's say. That is the epicenter. So on the surface, epi. There is the epicenter of the earthquake. The crack on the surface where there's movement, we already talked about that one. So right here, that crack where there's movement, that's the fault. We already talked about what that was. So when we talk about the epicenter, and you say, oh, the epicenter was in, I don't know, Seattle. Does that mean the fault, the crack in the surface, was in Seattle? Not necessarily. The epicenter is directly above the focus. The fault could be there if it's a strike-slip one, but if it's a normal fault like this, or a reverse fault, normally that crack in the surface isn't at the epicenter. So just kind of think about that when they say the epicenter was in this certain place. You know, it's not like, oh, I'm going to go there and see the big crack. It might just be where a lot of the damage was. Well, why is a lot of damage at the epicenter and not at the fault? It's because that the earthquake also gives off seismic waves. So let me change my color. So the focus is where it starts, so then we're going to have waves that radiate out from the focus. And where is the first place that these waves are going to hit the surface? They're going to first hit at the epicenter. So that's why usually the damage is the worst at the epicenter, because the waves are the strongest there, because they've gone through the least amount of rocks. They're still really strong waves. So these are seismic waves that I just wrote down. We'll be more specific in the next section. These are going to be called body waves, but for right now, we can just call them seismic waves. And then the last part that we should probably put on there is the fault plane. The fault plane, I'll do it in a different color actually. The fault plane is this whole surface underground where the plates are sliding next to each other. So fault plane, that's the whole surface underground where the plates are sliding next to each other. So your picture should look like that. Then the definitions, I just put on all in this sheet, and if you want to pause it to write these down, you certainly can. The focus is the point underground where the stresses first cause the ground to break. The epicenter is the point on the surface directly above the focus. The fault plane is the whole surface underground against which the two sides of the fault slide. And that's it for our basic definitions. Our next section is going to be on the earthquake waves. So we're going to be finally getting into our really the meat of this, and then we can start talking about what we can do about this.